Okay, so yesterday we were discussing the transport, the contaminant transport from so we were looking at the development of the transport model within the system here. So we are looking at transport in this z direction. So the equation we derived yesterday, and this is this water here. Is rho rho A2 by dou T equals dA3 divided by epsilon plus Ka32 star into dou square by dou V square. So this is the this is called as the in general is the domain equation or the process that is happening in the domain. So the domain is this, the sediment is the domain, the process is happening, this describes the processes happening here. So this term here epsilon 2 plus K32 star rho 32 is called as the retardation factor. So we defined it as RA32 is called as the retardation factor. So this retardation of A between 3 and 2. Okay. So which means that this equation, equation 1 describes what is happening in the bulk of the sediment. Of the domain, and that is why we call it as the domain equation. You can of course have transport happening in y direction and in x direction as well. You can write the main equation for that also. So this will extend into that. That is possible. As a domain equation, we will have all that. Okay. But for the purposes of this, we will not do that, because we will have some simple mathematical solutions for whatever we are doing here. So you can't have simple analytical solutions for 3 dimensions and 2 dimensions. So that needs separate tools for that. I will talk about that also. So now here we need 2 boundary conditions. And 1 initial condition for this to solve this. Yeah. So we are, our domain starts here. This is z equals to 0 and it goes down. This is how we have defined our system. So let us talk about the first. Let us talk about the boundary condition at z equals to 0. What could be the boundary condition at z equals to 0? So this equation here, this, so one has to look at what is happening at z. So boundary conditions are all written. Usually boundary conditions are written at z at a particular location at all time greater than 0. This is how it is written. This is the full definition of a boundary condition, which means it must be applicable at all time. Okay. So what is applicable at all times in this particular boundary? So, there are several possibilities, but in this case material is going out at that boundary. So, we can use what is called as a flux boundary condition. Boundary condition can be anything. Say we can have flux boundary condition is one is that we are assuming that at a steady state is at a there is no accumulation at the interface. This is something an assumption that we make all the time. So, whatever is coming from here is going here, okay, at the interface, which is z equals to 0. Material is what is being brought from one side of the interface is leaving the other side to the other side at the same rate. The rate at which it is brought in is going away there. What is the rate at which this is this? So, let us call this as 1 and this call this as 2. What is the rate at which material is brought to the interface, or the flux? In other words, its normalized rate is flux, area normalized rate is flux. Yeah. So, what is the flux of chemical brought in to the interface? You understand what I am saying? So, one is the process bringing is the flux bringing A to the interface, and 2 is the process is the flux taking A away from the interface. So, something is happening on this side on this side, and something is happening on this side, that is bringing some transport process is bringing material to the interface, another transport process is taking it away from the interface. So, what is it on the side 1, which is on the sediment side? How do you describe what is the flux? How do you describe the flux for material bringing material to the interface from below? What is the process? What is the mechanism? Diffusion. So, what is the diffusion flux? It is minus of dA3 d rho A2 by dz at z equals to 0. You notice that the R term is gone now because we are not. It is at the interface, just before the interface. We are talking about, see there is some material here and there is some material, yesterday we are talking about this particular region, which is no longer interacting with this, it is just about to get out, but this is diffusion here. So, it is no longer, it is not, it is just a transport process, it is no longer, it is already finished its interaction with the solid. So, that this thing is retardation is not accounted for at this point. What is on the other side? What is on the water side? How do you define flux on the water side? As we have been seeing last few classes. Huh? It's a mass transfer coefficient K23 multiplied by rho A2 at z equals to 0 minus rho A2 infinity. This rho A2 infinity is this is the boundary condition that we apply. This is at z equals to 0. So, what is the other boundary conditions that we can write in this system here, which is far away from the interface? So, we have several possibilities. We have at z equals to some finite height distance. Now, this finite distance, it has again it is at all time greater than 0. It should be valid for all time greater than below. How can I say all time greater than 0? There's at some particular location it has to be true every time. But in this scenario, I do not think there is a particular location away from the interface where it is going to be a known fixed value, a fixed condition, a fixed concentration, for example. So, one particular thing there are a lot of different conditions. So, we can go through a set of these conditions. For example, in this case, one thing that you know for sure is that people use this condition called as semi-infinite boundary conditions, where at z equals to infinity, what is there at z equals to infinity? What do you mean by z equals infinity? Z equals infinity means it is very far away from the interface. So, to write down what is there here, rho a2 at z equals infinity will be rho a2 0, and rho a2 0 is the initial condition. The initial condition is at time t equals 0 at all z. This is the condition for that, which means that everywhere throughout the system at time t equals 0, this is the initial conditions. Okay. Well, this need not be true. This at all z is not necessarily true for initial condition. At a given z, what we are meaning it at some z. So, it could be that at all z we can have rho a2 equals to rho a2 0. This is some initial conditions, which means. So, when we are writing this statement, we are assuming that it is uniform everywhere throughout the system. Rho a2 equals rho a2 0. This is one particular case where you can look at it. Yeah. So, what we are saying at z equals to infinity, rho a2 equals rho a2 naught, is that somewhere very far away from the interface, where interface is where all the action is happening, transport is happening, very far away nothing is happening, no movement is happening, because we see yesterday's this thing, the depletion occurs from the interface. So, the moment material from near the interface gets out first, and then there is diffusion gradient set up inside and so on. So, by the time that gradient reaches significantly far into this, it's a long time. So, you may not want to solve the problem till that time. Your interest time in region of interest of time is much below that. So, we will see that. So, this is called as a semi-infinite boundary conditions. Is used a lot in this kind of transport problems. Boundary conditions, which assumes there is nothing called as infinity. Infinity is some large number, and it essentially means that at infinity nothing is happening, no change is happening, and that is your infinity, whatever it is. We do not really know what it is, we are assuming that it is that. So, semi-infinite boundary condition is this. The other alternatives, let me just write the solution for this first. So, now we have the solution for this equation. You solve it using Laplace transforms, and you will get the equation that you get, rho a2 z of time equals rho a2 0 into error function of RA32 into z divided by into t plus, I will write it below, plus exponential of It's a pretty big equation. Yeah. The solution for this is you can use Laplace transform and similarity transforms to do it. Several possibilities. Okay, so it will give up this big solutions. Okay, now the flux at this is now a function of time at z equals 0 is you can use either of the two terms. The flux you can calculate once you calculate this expression you have. This expression, if you notice, is a function of z and t. T is here, z is here. Z and t appear in this equation. The other parameters in this equation are, we will write down that. Is rho A2 0, K2 and diffusion coefficient. These are the 4 parameters that we need. So, the flux itself you can use either of these two equations at the interface. You can use either Ka23 multiplied by rho A2 at z equals 0 minus rho A2 infinity, which means that I have to take this equation and put z equals 0 in this equation. In equation 2, I have put z equals 0 and whatever I get multiply that by Ka3 minus z, or I can do minus of dA32 d rho A2 by dz at z equals 0. So, I take the integral first derivative of this equation 2 and put z equals 0 there multiplied by the diffusion coefficient. Either of this is possible, you should get the same expression doing this. If you are interested, I can give you the solution for this, but right now for this we do not need it. So, here rho A2 0 is the initial boundary condition. So, what we have initially is we have some contamination, right? We have some contamination. We are assuming that this contamination is uniform as a function of depth. Okay. So, but we are talking about rho A2 0, right? So, rho A2 0 is a pore, is the concentration of A in pore water. How do you get this? This is predicting a model. So, scenarios are like this. So, you know there is a contaminated sediment site, you would like to know what is the flux of chemical coming from there into the water, which means these are the things that you should know in order to be able to calculate equation 1 or equation 2 or equation 3. So, rho A2 0 is data that you need. How do you get rho A2 0? You have to get rho A2 0 from some measurement, and what is the thing that you can measure? Compared to sediment, for sediment quality, what do you measure? What can you measure? You have to go and measure. You need monitoring here. Monitoring. What do you monitor? What do you measure? What is the measurable quantity here? The measurable quantity, when you measure sediment, we did sediment extraction, right? What do you measure there? You take a sediment sample, you measure something. What do you measure? If you recall your analysis methods, I take a sediment sample, what do I do with the sediment sample in order to extract? you extract with something. You take some amount of sediment either with circular extraction or ultrasonication. We take a certain amount of wet sediment and you add some solvent and you extract. What are you extracting here? Which fractions of chemical are you extracting? The chemical that you are extracting is from the solid phase or the pore water? Huh? Solid phase or the pore water? You are taking wet sediment, dumping it into a container with circular extraction or water and adding solvent and extracting it. You are extracting both. So, which means that you are doing both rho A2 V2 plus WA3 M3, both of these are happening. But what are you reporting this value as? When you extract everything, you are reporting this as WA3 only, but you are reporting it as WA3, we are reporting as, the reason we are reporting it as WA3 is, we are reporting it as a mass of chemical divided by the mass of dry solid. So, this is a bit tricky because what we measure is not just W. The theoretical W we say is only the solid phase. What we are measuring is the total concentration. So, what we are measuring really is this entire thing. Yeah. So, let us call that as WAT. WAT is the total measurement. But our measurement WAT, let us say I am reporting a value of WAT, I am reporting a value of 100 milligrams per kilogram. What I am reporting is 100 milligrams of kilogram dry. Okay. So, this 100 milligrams is coming from both solid and liquid phases, but I am reporting it as on the basis of dry. Yeah. So, if I know what is the dry mass, that is what I am reporting as, because that is unchanging. Water content is changing, so I am reporting as dry. So, I think this is a bit tricky to get a hold of, but this is what it is. So my mass balance is this, is rho A2 into V2 plus WA3 into M3 equals this. Okay. So, we are talking about this. So, in other words, we are saying the rho A2 V2, rho A2 0 V2 plus WA3 0 M3 equals WAT M3. And we are also saying, if you use the local equilibrium assumption, that these two are in equilibrium. Rho A2 is in equilibrium with WA3 0, which means that rho A3 equals Ka32 star. So, I can write this as rho A2 0 into epsilon 2 into into V2 plus M3 into Ka32 star. So, this is a number that we are measuring, this is a measured number, okay. This is what we are measuring. So, in this equation we will write it as rho A2 0 equals WAT into M3 divided by V2 plus M3 Ka32 star. I am going to write it in the next page. if I divide both sides by the total volume, I will get WAT rho 32, this is the bulk density, divided by epsilon 2 plus rho 32 Ka 32 star. What is this? This is WAT into rho 32 divided by RA 32. This is the you get the pore water concentration at any point. It is not just 0. Right now we are writing 0 because that is what we need, but this value is what is measured. So, when this we assume is whatever is the value of the sediment concentration loading at whatever time you are interested in starting the simulation. So, this bulk density multiplied by the actual measurement WA3 WAT is the measured loading of A in the sediment. We remove the subscript T and we put WAT there, so that just to indicate that. For very large, so let us take for example, if you are taking some compound which has a log is a Ka32 is KOC FOC. If you take some compound which has KOC of say 10 raised to 4 liters per kilogram and an FOC of say 0.10%, yeah, this is 1 10 raised to 3 liters per kilogram Ka32, yeah, equals 1 meter cube per kilogram Ka32. The bulk density of sediment, it ranges between bulk density of the density of water if there is no sediment. So, only water, density of water is 1000 kilograms per meter cube. If you keep adding solid, the mass goes on because the particle density of solid is around 2000 to 2500. So, the bulk density of sediment is usually higher than 1000. So, let us say it is 1500 kilograms per meter cubed. If I put these two, so let us say it is 100 and let us say the WAT is 100 milligrams per kilogram dry sediment. Okay. This equation here is WAT into rho 32 epsilon, epsilon, what is the maximum value of epsilon? Maximum value is 1, you are not going to have 1, you are going to have somewhere between 0.4, 0.5, let us say it is 0.5, so epsilon is 0.5. 0.5 plus in this denominator we have 1500 multiplied by 1. If you look at this denominator, a lot of times this denominator, this value is much greater than this. So, you can neglect this. So, then this equation for sediment systems, for very dense systems and with Ka32 very large, this you can approximate this equation. You can approximate WAT rho 32 by epsilon 2 plus Ka32 rho 32 is WAT rho 32 divided by Ka32 rho 32 . But the accurate representation is this, but you can approximate it to this for certain systems where the porosity, the product of the bulk density and Ka32 is very huge. It won't make a big difference if you remove that. Okay. WAT divided by Ka32. In essence, we are saying that when you are doing WAT measurement, water is so small that does not matter, you can take it as WA3. So, what we are essentially doing is we are doing WAT is approximately equals to WA3. This is what we are doing. This is what this means, because this is what we did when we want to calculate pore water concentration. We are just directly doing this, right. This is equilibrium, rho A2 0, rho A2, this is rho A2 equals this equals this. Yeah. This is what we did in our calculation in the beginning when we are doing equilibrium and all that. Okay. So, now the next thing is the when you take measurements, which we did not discuss this when we were doing the measurement part. When we measure WAT, normally see we have this, our system of interest is here. So, we have a sediment that is contaminated, this zone, right. There is a certain distance to which it is contaminated. How will I take a sediment sample? So, my assumption that rho A2 equals to rho A2 0 at all z is the initial condition at time t equals 0, assumes that this is uniform, but it need not be uniform. Yeah, most likely it will not be uniform. Why will it not be uniform? Yesterday we discussed that it cannot be uniform, because as sediment starts from one end, the contamination starts from one end, it is diffusing inside the sediment. So, it will never be uniform, it is going to be decreasing, it is going to be very high at the top and it is going to be decreasing towards the bottom. Okay, that is one possibility. So, this assumption is very it is not a good assumption. So, you have to measure rho A2 equals to rho A2 as a function of z at time t equals 0. This is the correct representation of it. So, if we are now fixing that rho A2 0, rho A2 0 z is the same for all, but that need not be true. Okay. How do you get this data? We are getting rho A2 0 from WAT, which is a measured value. So, how do you get this data? So, if you want to get, you are getting a profile of sediment loading rather than one location. Okay. So, this is what when we want a profile, what we are saying is that I would like to have measurements made at every distance as z equals to 1, z1, z2, z3 and so on. I need to know what is the value of WAT at each of these locations. How do you do this? To do this, your sampling procedure for the sediment is not you just go there and pick up one sample of sediment. It needs to be a profile, and this profile is obtained from what we call as core sampling. And this is true for soils also, because continuously in these systems transport process is going on, transport is happening, diffusion is happening, degradation may be happening, other things also may be happening. So, we will see some of those things. So, we do what is called as core sampling. So, core sampling, usually we put a tube into the sediment and we pull it out. So, it is a very tricky process. The moment when you put a tube inside, it is sometimes difficult for the tube to go inside. So, but this is for sediments it is reasonably wet, so it is fine. For soils and all that, it will not go, you have to hammer it in, you have to send it in and then loosen the thing and then pull it out. So, here when you push it in, this is like water, almost this is cohesive material. So, you have to seal the top. So, which means that you are almost putting a vacuum. So, when you put a tube into water and seal the top, when you close the top and pull it out, the water column stays intact. So, you have to do the same thing here, you have to seal it off and then this core comes out. This core will now contain little bit of water on top. This is the water here, and this water is there in the water, river or lake or wherever you are sampling, and then this is the sediment. So, how do you measure this sediment? Now, you take out this pore water out and then you slowly push the sediment out and take one layer by layer. So, you get a value of WAT for say a 3 mm thickness layer of sediment. I am just arbitrarily saying 3 mm, it could be 1 mm, 2 mm, it is to the extent to which you can divide, you can push out and divide. This is not an easy process to do, because when you are pushing it out, so extruding it out now, sometimes these layers will mix. At the wall they will stick and the one in the center will get out. So, when what you are getting may be a slightly mixed layer. So, these are all errors that will come in this thing. So, what you will get here is this data like this. So, z equals to 0, if you draw, and this is the concentration rho 8, this is the concentration of WA3 of T, you will get some value like this. So, the data from this will look like this, you will get something like this. This is the first layer, this is the second, this may be the second layer, this may be the third layer, this may be the fourth layer, this may be the fifth layer, and so on. It is arbitrary, it can be arbitrary. If you are assuming that there will be a nice gradient, this highest top, the one closest to the surface will be highest, and then it will keep on decreasing. But this can be arbitrary, the value of WAT at, so I am drawing some kind of a bar chart here, because this is now a composite of, this is 3 mm, 6 mm, 9 mm, 12 mm and so on. So, this value corresponds to this layer between 0 to 3 mm and so on. Okay. So, when you are doing the modeling, when you are representing this as this thing, it is your choice. You can say that I will call this as 3 mm, I will say between 0 and 3 mm the concentration is the same, or I will draw a point like this, and then I will fit a line curve through this, and then I will give an equation to that. That is one possibility. But more often when you get these kind of gradients, our model that we solved is for uniform concentration. You cannot apply this and go there. This is a discrete distribution of concentration, right, corresponding to WA3 you will get. So, for rho A2 at z equals to 3 mm, you will get WA3 at z equals to 3 mm multiplied by rho 32 divided by the RA32. This is the calculation that we do. So, you can also have rho A2. You can, from the WAT you can calculate rho A2, you will get a profile of rho A2 also here. You cannot solve this analytically. The analytical equation we presented is only valid for concentrations which are uniform. Okay. When you get these kind of systems, it automatically you have to do a numerical solution. You have to take this and do a numerical solution using any of the methods available. When you do a numerical solution, you automatically take a numerical step, a delta z and a delta t that you are looking at. So, when you take delta z, if you have data for some delta z here already, you take that same step. So, which means that within that step you are calculating that. Anyway, you do not have values for rho A2 within a resolution less than 3 mm or whatever you are measuring. So, you might as well do it this way. So, this is the way it is done. Now, just a small point, why do we have, when we say gradients, initial gradients, we expect that since contamination is highest at the surface and it is going out, you expect a gradient to be in this direction, this kind of system. Why have I drawn this haphazard this kind of system? Any guesses? Very often you will find profiles that look like this. If I am drawing like this, profiles may be like this, z equals 0, there is nothing in the top, and then there is a big, it may look like this. Can you guess why it may look like this? In the sediments. This does not happen in soils, it happens in sediments only.
That has gone into water at the top.
Yeah, but you would expect that it is still a diffusion based process, the gradients are preserved. Why like this? I agree what you are saying, but there is a big zero thing here. What you are saying it is true. See, normally this is what you would expect. Suppose I start with a constant concentration, this is time t equals 0. As time progresses, what you expect to see is something like this will happen. and so on. So, the time is increasing, So, in the semi-infinite calculation, one of the things you have to do is here at this point the rho A2 is still rho A2 0 at this point at your maximum z, whatever you are calculating. Yeah. So, in the model, when you in the solution of the model, we saw that there is a z term there, right. There is a z term here, there is a z term here. That z you have to put it into the model. So, that you are this is the z axis, you are calculating it for different z's. So, as long as the time for which you are calculating, computing ensures that you are still not reached that point. So, let us say that your profile looks like this, it is no longer valid, semi-infinite condition is no longer valid. Yeah. You can only solve the semi-infinite conditions for times which are where the diffusion process has not reached that the edge of your system. Anyway, this is what you expect when the diffusion process is happening. So, there is depletion in the top. So, you are seeing that there is loss here and there is decreasing order, but what I am saying is looks very random. Yeah. There is nothing in the top section. Why can this happen? Why will this happen? Can you guess why this happens in sediment systems? This is not related to anything we have discussed so far. This is something which is very very different from what we have discussed. Just think about it. So, in rivers, this happens mostly in rivers, it does not happen in lakes. It happens in rivers, it can happen in oceans, in sea coast. No, there is no accumulation, it is loss, complete, there is no. So, let me give you another hint. What if you see a profile like this, what does it mean? This is what you would expect to see if the contamination is happening, but then you see this one layer on the top which is there is nothing in that, no contamination in that. What does this mean? What could this mean? Top layer carried away with water, you should see something like this. Can you make another guess? The reverse of that, what you just said is the reverse of that. Material, top layer will get carried away with water, that is erosion. But this part is because erosion is happening somewhere else, that can get deposited here. This happens a lot when you have heavy rainfall, erosion happens, a lot of sediment gets carried away, but it gets deposited elsewhere, which means this layer can get carried somewhere else and it drops somewhere else, which is the reason why you cannot go into a sediment and take a top layer sample. I cannot take a small bucket and pick the top layer and say declare that there is no contamination, there is contamination sitting below, which is the reason why you have to take a core sample to a certain depth. So, the modeling helps a lot. The modeling will not give you accurate results, but it gives you a very nice estimate, because we are talking about long time scales. It gives you an estimate of where you are. You can give you some very good reasonable estimate, provided you have all the other numbers estimated accurately. So, we will stop here. The other parameters that we talked about, we will go one by one. So, this is the most important one we talked about, rho A2 0 estimation. The partition constant, this is the diffusion constant. So, all these terms, so Ka32 we get from a correlation. Retardation factor, we need to know the bulk density and the partition constant, okay, which you can get if you get the sample of the sediment, you can measure the partition constant. You know which compound you are looking at, if you know the organic carbon fraction of organic carbon, which you know how to measure, and you know the KOC of that compound, Ka32 you can measure, you can estimate, and therefore all this. Bulk density also you can measure. That is the reason of having a core, because bulk density will change the moment you take a grab sample, because you take a grab sample and put it on this thing, it is all gone, it is all open now, you are not retaining the original structure of it, but you can measure the bulk density, in situ bulk density, by grabbing a core and then carefully measuring what is the amount of water, what is the volume corresponding to that mass and all that. You can do all those calculations based on that. So, one other thing is, because it is a sediment, when you are taking a core, it is very likely that the porosity and the retardation factor of this layer is very different from this layer. often the sediment is not, composition of sediment changes even within a few feet. Okay. So, the core will allow you to get that. In that case, this model will become entirely everything will go into the derivative. So, it will become, if you are assuming everything to be a function of space, all your thing will go inside. So, you have dou rho A 2 by dou t equals, it becomes dou by dou z, everything goes inside, dA by r into dou rho A 2 by dou z. This everything goes inside the derivative, which means dA is now a function of z, r is a function of z. Okay.